Okay, so last time we discussed two important comparison theorems. The first one was the just naive comparison theorem. The other one was the limit comparison theorem. So basically, the idea was you're just comparing a series with another series, and and those two comparison theorems were only useful when your series is only involving the non-negative terms. If your series contains infinitely many negative terms and the positive terms at the same time, then you cannot use those two comparison theorems. So today we're going to discuss in the case when your series contains the infinitely many negative terms. So, for instance, like there can be a series which is alternating, so positive terms and negative terms and positive terms and negative terms. So for such series, what can you say about the convergence or divergence of the series? The first theorem, in order to answer the question, this is the first useful theorem that comes in our hand. Okay, so this theorem gives us the vague idea how to deal with the series that contains infinitely many positive and negative terms. It says like this. Well, suppose that we have a series. This is the given series, and this number may be positive or negative. So anyway, but we can actually convert this series like this. And this new series was obtained by taking every term by an absolute values. Okay, now this series is a series that contains only non-negative terms, right? And suppose that for some way, so we were able to show that this guy is convergent. In that case, we are also safe to say this guy is also convergent. Okay, all right. So, proof. For any number, the number plus absolute value of itself is always, this is always non-negative. And this is always bounded by 2 times absolute value of the number, right? So these inequalities are obviously true. So therefore, now we consider a series. Now let us consider the series. This is a series of non-negative terms. And since we have this inequality, therefore, this is also bounded by this. Okay? But because of this hypothesis, so we already know that this one is convergent. So this guy also must be convergent, right? Because any constant multiple times convergent sequence, this convergent series is also convergent. Okay. Right. So this is therefore, because of the comparison theorem, this is a series of non-negative terms, and this is another series of non-negative terms. So therefore, definitely we can make use of the comparison theorems, right? So since this is convergent, therefore this guy also must be convergent, right? Okay. Now I want to consider this. What if I subtract this guy by this? I want to consider this is a number, right? Because we already know this is convergent, and this is also convergent. So what happens if we subtract this guy by this? Then, because of the definition of the infinite series, so this one should be understood as the limit of the partial sum sequence, right? So n to the infinity, so j from 1 to n, this is a partial sum sequence, aj plus absolute value of aj, and minus another limit of from j, no. Sorry. This starting index should be 0 because, this is 0. Okay, so sorry, doesn't matter. Well, anyway, I messed up. Okay. Okay, sorry. I just realized I messed up the indices. I know this doesn't make huge difference, but since the original statement is about the starting index is 1, so 1, 1, 1, 1. Okay, good. All right. And this is convergent, and this is convergent sequence, and this is another convergent sequence. Therefore, subtraction of the limit of two convergent sequences should be this minus this, and this is just so this is actually the so we have the parenthesis. So let me introduce a huge parenthesis over there, and the difference between these two. So actually this is about the difference between two finite series, right? So which is just aj, and this is from 1 to infinity of aj. Okay, all right, so this guy equals to this, but we already know this is finite, okay? So this is also finite. In other words, this is convergent. Okay. So this is how, so this is, this gives us the basic tool in order to deal with the series that has both positive and negative terms. So such as this one. Let's take a look at this series. Obviously, as n goes to infinity, the sequence tends to 0. So this test is the test for divergence. But however, I cannot use the neither comparison theorem nor the limit comparison theorem because of this alternating factor. Well, so this is plus and positive, negative, positive, negative. So positive number and negative number, they are alternating, right? So therefore, we cannot tell anything about the convergence or divergence of the series. But however, I know that so I can prove that this guy is also convergent. Why? Because let's take the absolute values inside of this summation. Minus 2 to the n times n, and then it's going to be from n to 1 to infinity. Then this is 2 to the n times n. Okay, all right. And I am pretty sure that this is also convergent, right? Why? Because this is clearly less than 1 to infinity of 1 over 2 to the n's, right? Okay, and this is what? This is a geometric series whose common ratio is just 1 over 2. Therefore, this guy is convergent. Therefore, this is also convergent. So therefore, this guy, since this guy is convergent, therefore, the original series without absolute values also must be convergent. Okay. Right? Yeah. Okay. All right. So this theorem is somehow very useful. So especially when your series contains negative and positive number. Well, just one more thing to add. So yeah, obviously the converse of the statement is not true, right? Right? Because I mean, there is a series that contains both positive and negative terms, and which is convergent. But when you take the absolute value of the series, that may not be convergent. There is such a series. And today we are going to talk about that. Okay, so yeah, so this involves a lot of assumptions, but let's just talk about them one by one. I have an infinite sequence, and which is strictly which is non-negative, right? And because of these inequalities, it looks like this sequence is a decreasing sequence. I mean, non-increasing sequence, right? Okay, so AN is the decreasing and non-negative sequence, and plus there's another assumption, and AN is tending to 0. Okay, let us assume these two things. Now, the series in question is this. This is an infinite series, but this is not positive series. This is clearly an alternating series. Also, positive number and negative number, and positive number and negative number, right? Because of this alternating factor. And it tells us this one is also convergent. So this is what we call the alternating series theorem. So that means so I feel like this is slightly more relaxed condition because, when your series contains only positive or non-negative numbers, then the sequence tending to 0 is not suffice to show that series is convergent. But in this case, if your series is tending to 0, if your sequence is tending to 0, and if that is decreasing, then the alternating series obtained by the sequence is also convergent. Okay. Okay. All right. Good. Okay. So what now? Okay. Now I want to prove this. I want to consider the partial sum sequence from this infinite series. Is from J1 to N minus 1 to the J's and AJ. This is the partial sum sequence obtained from this infinite series. And I want to talk about these two, well, I should say the subsequence of this sequence. I mean, this is a sequence, right? This is partial sum sequence. And I want to talk about a subsequence out of this sequence. Hey, what do I mean by subsequence? This. We consider this as two ends. So what is this? So this is a subsequence obtained from this sequence, and this new sequence only contains the even index terms from this sequence, right? So we're more explicitly, so this is S of S2 and S4 and S6, da da da. So this is a subsequence that contains only even terms from the partial sum sequence. And we also consider S of 2n minus 1. This is S1 and S3 and S5. So this is another sequence that contains only all the index terms, all the index terms from the partial sum sequence. And I want to prove a couple of things from these subsequences. First, this guy S2n is a decreasing sequence. Okay, so what is this? Why? Because, so in order to show if any sequence is decreasing, then what you're supposed to do is just try to figure out the difference between two consecutive terms. Right, sorry, in this case, yeah, this is the difference between two consecutive terms from this subsequence, right? Okay, and what is this? Hey, so this is the summation from A1 to A2n. This is summation from A1 to A2n minus 2, right? And since we are taking the difference between these two, so this is going to be A2n minus A2n minus 1. Right, yeah. Because this is an alternating, and since this is an even, so since this is even term, so this is positive. This is also, this is negative, right? Okay. And, okay, now what? Oh, now we know that this is AN, this original sequence was decreasing sequence. Therefore, if you take the difference between these two, then this guy should be slightly greater than equals to this one, right? So this is non-positive number. Right? Right? Okay. The second, this subsequence is bounded below. This is S2n, and this is minus A1 plus A2 minus A3 plus A4 minus A5 all the way to plus 2n minus 2 minus 2n minus 1 plus A2n. Yeah. For educational purpose, yeah, I intentionally written expanded S2n in terms of ANs, just like this, right? Now, I want to group them just like this. You have to remember that the sequence AN was decreasing sequence, right? So I am pretty sure that this is positive, right? And sorry, non-negative. And the second parenthesis is also non-negative, right? And and this is also non-negative. And this is also, the last one, this is also non-negative, right? They are all non-negative numbers except for the first guy, right? So is greater than equals to minus A1, right? So, I mean, therefore, S2n is always greater than equals to the minus of the first term of the series. Okay. Now, so this guy is decreasing and bounded below. And when I say that, then that the monotone convergence theorem should appear automatically in your mind, right? Therefore, this first subsequence is convergence sequence, right? Okay, I'm going to do the exactly same thing for the second subsequence. Now, S2n minus 1. And this is actually an increasing sequence. Because S2n plus 1, okay, minus S2n minus 1. This is the subtraction between two consecutive terms from this subsequence, right? And this is minus A2n plus 1 and plus A2n. Okay. Remember, AN was a decreasing sequence, therefore, this guy must be positive, non-negative, so non-negative, right? And number 4, this subsequence is bounded above. Because S2n minus 1 is minus A1 plus A2 minus A3 plus A4 plus not plus, minus. Minus A2n minus 3 plus A2n minus 2 minus A2n minus 1. So this is S2n minus 1. And I want to group them just like this. Yeah, I somehow messed up. This doesn't look very beautiful. So yeah. Okay, yeah. So, and this first parenthesis is, yeah, remember, AN is also decreasing sequence. So this is non-positive. This is also non-positive. And this is also non-positive. And this last one, along with this negative sign, this is all, they are all non-negative numbers. I'm sorry, non-positive numbers, right? So therefore, everything is non-positive, right? Okay, so S2n minus 1 is increasing and bounded sequence, bounded above. Therefore, due to the monotone convergence theorem, this second subsequence is also convergent. So by the monotone convergence theorem, the first and second subsequences are convergent. So we define them which is L1 and S2n minus 1. I will define this guy to be L2. Okay, all right. Now, what remains to show is this. Okay, we have these two limits, and if we were able to show that these two numbers are actually the same number, then that should be the limit of the original alternating series. So L1, I want to subtract these two numbers, which is this minus that. But since these are two convergent sequences, so it is okay to say that this is Sn minus S2n minus 1. Right? But what is this? This S2n and S2n minus 1 can be written as A2n, right? Right? And finally, okay. And now this is time to make use of this last assumption. And since this guy is tending to 0, so this guy also should be 0, right? Okay, so why is it so important? So from this original partial sum sequence, so we were able to take these two subsequences, right? And these two subsequences, it turned out that those two sequences are converging to the exactly same number. So therefore, this one, the original sequence, or the original partial sum sequence, should be also converging to the same number, right? Is B also L1 and L2. So this ends the proof. So this is the alternating series theorem. So sorry, what is that? Yeah, alternating series theorem. So what is an alternating series? So if your series will change its sign term by term, then so the first one is positive and the next one is negative, and the next one is positive and the other one is negative. So if the sign changes one by one, then we say the series is alternating. We say the series is an alternating series. And if you're alternating series, suppose that you have an alternating series, and if the number, if the absolute value of the number is decreasing, if the decreasing and tending to zero, then we can say that alternating series is actually convergent. This is one of my favorite example in this entire semester, and it goes like this. Is it an alternating series? Yeah, this is an alternating series, right? Because the first one is positive and the next one is negative, and the other one is positive and the other one is negative, right? The sign changes on and on. So this is an alternating series. Now, let me check if this series is actually satisfying the conditions given from the alternating series theorem. If you take, ignore this alternating factor for now. So, if you take the absolute values to the sequence behind this summation, then this factor, this number, 1 over n, is clearly decreasing, right? And which is also tending to 0, right? Therefore, the sequence is satisfying the conditions given from the alternating series theorem. Therefore, this one must be convergent, right? Yeah, I really like this one. So I gave this series, a name. I say this is an alternating harmonic series. So this is so interesting. Why? Because, this guy is convergent due to the alternating series theorem. But if you take the absolute values to the sequence, then suddenly this guy is going to be just a harmonic series. And harmonic series is very well known to be a divergent, right? So so this example can be regarded as a counterexample of why the converse of this theorem is not true, right? Okay. Okay. So, sorry, let me digress a little bit. This one is convergent, but the question is, this number is converging to which number? Yeah, that is actually a very interesting question, and it turns out to be this number is converging to natural log of 2. Wow, isn't that amazing? 놀랍지 않으세요? Yeah, question? ln of 2. ln이 내추럴 로그 오브 2로 수렴을 하고 있어요. 이게 되게 재밌는 증명인데 이게 상당히 증명하기가 까다롭거든요. 이거를 중간고사 지나서야 증명할 수가 있어요. 이게 왜 ln of 2로 수렴하는지. 사실 되게 재밌는 수열들이 되게 많이 있거든요. 여러분, 그러니까 리만 제타 펑션 같은 것도 있잖아요. 그렇죠? 그런 거 아세요? 뭐 인파이나이트 시리즈인데 1 over n이 아니라 1 over n 스퀘어 같은 거. 그런 게 뭐 파이 오버 뭐였나? 잘 기억이 안 나요. 그런 걸 수렴하는 거 증명하는 거 막 유튜브에 많이 있잖아요. 그렇죠? 혹시 그런 기억 안 나세요? 그런 거 사실 되게 중요한 증명들인데 그거는 푸리에 시리즈를 배워야죠. 그건 증명입니다. 하여튼 되게 재밌는 인파이나이트 시리즈들이 많이 나오고 걔네들이 어디로 수렴하고 있는지 그 친구들이 왜 무리수인지를 증명하는 거는 정말 재밌는 증명들이에요. 예를 들어서 여러분 거기 오일럴 컨스탄트 있죠. 자연상수익. 그게 왜 무리수일까요? 혹시 그런 거 증명해 생각해 본 적 있어요? 그렇죠? 생각해 본 적 없죠. 사실 그게 되게 어려운 증명이에요. 파이가 왜 무리수인지 혹시 그 증명 같은 거 생각해 본 적 있어요? 네. 하여튼 그런 재미있는 일들을 이제 남은 시간 동안 계속 하도록 하겠습니다. 오케이. Oh, sorry. Okay, back to the track. Uh, this theorem it is not in the part of this our textbook, but I really want to mention about this. So this is called the alternating series error estimation. Okay, let us suppose this. I have an alternating series, which is, and that is satisfying, say that that is satisfying all those conditions given in the alternating series theorem. So this guy is non-negative and decreasing. And okay, so this one, now let us say well, since this guy is satisfying all those conditions, so we know that this is convergent, and we give this guy a name. So let me say this is an S. Then I want to find the upper bound of this number. So I mean, so S is the true value. S is the value that we are tracking for. And Sn is approximation, right? Which is the partial sum, right? Because, well, so we are finite beings, so we cannot compute a number infinitely many times. So therefore, we actually, so in order to find a nice approximation of this truth value, then we have to truncate this infinite series at some certain point, right? That is Sn, the partial sum sequence. So this is the true value, and this is our approximation. And if we can find the upper bound of this guy, well, reasonably nice upper bound of this guy, then that is going to give us the error estimation of our approximation. The difference between the true value and our approximation should be the error bound. 오차의 한계를 우리가 알 수가 있겠죠. And this is bounded by an plus 1. This is so useful fact, so easy and so useful fact, but the proof of this one is not provided in our textbook. So let me have a couple of minutes to justify this. Why? Because so if you pinpoint each of these partial sum sequences on the real line, then, well, if this is S1 and S2 would be somewhere around here, and S3 should be there, and S4 should be there, and S3 would be here, and 5, like it goes like this, right? This is S1. If this is S1, and this one should be S2 because, well, S2 is minus A1 plus A2, right? So S2 should be slightly bigger than S1. And S3 would be somewhere around here, right? And this is short, and there should be S4 and S5. So it goes along like this. So which is alternating and is approaching to some certain point. And that approaching point should be the limit of this alternating series, right? And Okay, now let me say this is my Sn, and this is Sn plus 1. Yeah. For simplicity, well, we are assuming that Sn plus 1 is slightly greater than Sn, but this order can may be different. But I mean, so, okay. So for now, let me suppose that Sn plus 1 is slightly bigger than Sn. Then what we know is the S. This number, S, should be somewhere between these two numbers, right? These 2 points. So between Sn and Sn plus 1, there lies as the true value S, right? And the length between these 2 points is precisely An plus 1, right? So what is the difference between S and Sn? S minus Sn. So the distance between S and Sn is definitely smaller than length of this line segment, right? So this is how we justify this inequality. Right? Yeah. Okay. This is so easy and obvious, but well, this fact will be used in many times later on. So yeah, I believe this is the right time to introduce this. Okay, and so there can be cases such that even though the original sequence is convergent, but this one may be divergent, just like the alternating harmonic series. In such cases, we say the sequence, we say the series is conditionally convergent. However, if this series is convergent, then we know the original series is also convergent because of the first theorem in today's lecture, right? So if this guy is convergent, we say the original sequence is converging absolutely. So this is, in other words, we say is absolute convergence. So absolute convergence is even more stronger condition than not just regular convergence, right? So alternating harmonic series is one of the best example of the conditionally convergent series. Okay, so. Okay. And now we also want to talk about this series. Is it convergent or divergent? Yeah. For this time around, yeah, this is very hard to tell. And definitely this is a series of positive numbers. Right? So I feel like I can probably make use of the comparison test or the limit comparison test. First of all, let us just try to get. What do you think about this? Is it convergent or divergent? Convergent, right. Why? Yeah, I feel like this one is definitely convergent because, well, this is basically competition between polynomial over exponential. And, well, you know, exponential function is increasing way faster than the just polynomial function, right? So therefore, in the long run, the denominator will dominate over the numerator, therefore it should be convergent. So, okay, so yeah. So since this series looks like converging, therefore, but to which series we should compare this? Do we compare this? I don't know. Is this guy, well, less than maybe I can probably think of the geometric series whose common ratio is like 3/4. I don't know. Yeah, this is okay. It looks, even though this one looks like the convergent, but the finding the series to compare with is not easy. So therefore, when we are discussing series like this, then we actually need whole new mathematical machinery for whole new mathematical machineries. And this is the ratio test. Okay, yeah, sorry. I am running out of space, so. All right, so this is the ratio test. So ratio test is very useful when the comparison or limit comparison theorem does not work. Just case for just like this. And the ratio test goes like this. Suppose you have the series, right? And here, instead of the series, and we just take this sequence here, sequence AN, and we take the ratios between two consecutive terms, AN plus 1 and AN, and then take the absolute value, and we consider the limit of this new series, new sequence. And if this guy, suppose that this sequence is converging to some number, L. Yeah, so this is very hard condition, hard assumption, but suppose that this is true. And it says if L is less than 1, strictly less than 1, then the original sequence is converging absolutely. And if L, this number L, is strictly bigger than 1, then the series is divergent. But this theorem doesn't tell anything about the case when L equals to precisely 1. In that case, the sequence may be convergent or divergent, depending on case by case. But anyway, for those two cases, this ratio test gives us very important, very nice idea of the convergence or divergence of the series. Okay, okay. All right. I will try to prove A. Because of the assumption, AN plus 1 over AN. So this is L, and say that this is strictly less than 1. So yeah, I will draw some cartoonish picture. So this is number 1, this is 1, and this is L. and this is 0. Yeah, because, well, so this since we are talking about the series of the non-negative numbers, so sequence of non-negative numbers, so L cannot be less than 1. So L must be between 0 and 1, right? And I say, let me just choose some random point between L and 1. For simplicity, I'll choose just midpoint, which is 1 plus L over 2. So this is the midpoint between these 2 points, right? And this distance from L to this midpoint, I'm going to choose this guy to be my epsilon. So in this case, for an epsilon, so what is my epsilon then? So 1 minus L over 2. So yeah, 1 minus L, which is this distance, and divide by 2. So this one is going to be my epsilon. Yeah, okay. So this guy, now this is my epsilon. And clearly, this is a strictly positive number. Because, yeah, L was assumed to be less than 1, right? So, and so for this epsilon, since this sequence is convergent, I must be able to find a positive integer n such that if n is greater than this index, then this guy minus epsilon is less than, so this guy minus L should be less than epsilon. Oh, in this case, I should better say 1 minus L over 2. All right. This last inequality can be written as absolute value of an plus 1 over an is between L minus 1 minus L over 2 and plus L plus 1 minus L over 2. So if small n is greater than this number, this integer n, then we have these two inequalities, right? Okay, but however, I do not need both these two inequalities at the same time. I will only need this guy alone, this guy. And so let me simplify this guy. So L plus 1 minus L over 2. So this is simplifying this is 1 plus L everything by 2. Okay. I will call this number R. And here, since L was less than 1, right? L was less than 1. So this whole thing should be less than 1, right? Because this is this point, right? Okay, so okay, let me just cut to the point. So if small n is greater than n, then the absolute value of an plus 1 over an is less than this number R. Okay. So a large n plus 2 over a large n plus 1 is less than R. Am I right? Yeah, right. Because this index is definitely greater than n, right? And if index is greater than n, then this number is less than R, so which is guaranteed. Okay. So, okay. Is a n plus 1. Good. And a n plus 3 is likewise is less than R times an plus 2, right? But since an plus absolute value of an plus 2 is known to be less than this guy, so which is r squared times an plus 1. Okay, yeah, I know this is going to be a little bit tedious, but yeah, let me just one more thing. R times an less than r times an plus 3, right? But this is less than r squared times an plus 2. And this is also less than r to the third times an plus 1. Okay? And just keep going like this. Maybe you can use the mathematical induction. So n plus k, absolute value of n plus k, it should be r to the k minus 1 times a n plus 1. Okay? Okay. So I want to discuss about this infinite series. Index is beginning from large n plus 1. Then this one can be written as, in terms of the new index k, from 1 to infinity to a n plus k absolute value, right? And this is a series of positive numbers, non-negative numbers. So therefore, because due to the comparison theorem, this one is known to be less than, from k1 to infinity, r to the k minus 1 times a n plus 1. And remember, this is what? This is just merely a constant. So it doesn't affect too much about the convergence or divergence of the series. So what really matters is this common ratio. This is a geometric series, right? And this common ratio, R, definitely lies between minus 1 and plus 1. Okay? So this is a converging sequence. A converging series. Okay? Is convergent. Okay. So since this guy from n plus 1 to infinity is convergent, so therefore the original series from 1 to infinity, since adding finite remaining numbers does not affect the convergence or divergence of the series, so this guy should be also convergent. And you know what? This is precisely the definition of the absolute convergence. Okay. So yeah, so proof is done. Convergence absolute. Okay, yeah, I know this whole idea looks somehow confusing at the very beginning, but the idea is very simple. If this guy is converging to the number which is strictly less than 1, then we can actually compare this guy with a geometric series whose common ratio is less than 1. Okay. All right, good. And B. For B, we are assuming that a n plus 1 over a n is tending to L, and this number is supposedly greater than 1. So in this picture, this is 1, and there must be L somewhere around here. Now, this is okay. Say that this is our midpoint. Just choose any point you want. And yeah, for simplicity, I chose the midpoint. And the distance between L and this midpoint, I will say this is my epsilon. And in this case, this epsilon should be L minus 1 over 2. Okay. So for this epsilon, L minus 1 over 2, I know this is strictly positive because L was greater than 1, right? So this is strictly positive number. Then there is another integer, which again I will call n, such that if index is greater than this number, then absolute value of an plus 1 over an, everything minus L is less than epsilon. Yeah. Well, I should better call it L minus 1 over 2. This last inequality also can be written as this an plus 1 over an lies between L minus 1 over 2 and L plus L minus 1 over 2. So if index n is great, if these two indices greater than n, then we have these two inequalities. But again, I won't be needing these two inequalities at the same time. I will be only needing this guy alone. And this is what? This is just L plus 1 over 2, which I will call R. Okay, so I mean this point. So this is the coordinate of this midpoint. Okay, and this point is clearly greater than 1. All right, so a n plus 2 over a n plus 1 is, okay, since, okay, this guy is greater than R, right? In other words, we have this inequality. And by same reason, a large n plus 3 is greater than R times a n plus 2. But this is a n plus absolute value of a n plus 2 known to be greater than, so this is greater than a n plus 1. And a n plus 4 is a n plus 3, which is R to the third, a n plus 1. So likewise, repeating like this, a n plus k is greater than a r a k minus 1 and a n plus 1. So okay, now we want to talk about the limit of this guy. The limit of this guy is the same as limit of a n plus k, right? But if this guy exists, then this guy should be greater than this one, right? This is what? This is a geometric sequence whose common ratio is greater than 1. So this guy will blow up, go to infinity, right? This one goes to infinity, therefore this one goes to infinity, so therefore this one will also go to infinity, right? Positive infinity. Okay, so what kind of conclusion can I derive from this? So this means if absolute value of some sequence goes to positive infinity, then no matter what, I am pretty sure that the sequence, the limit of this sequence can never be 0, right? And this is clearly violation of the test for divergence. So this guy, in this case, this one should be divergent. Okay. Great. Okay. Okay. Now let me go back to our original question. Yeah. So I was having a hard time of using the limit comparison theorems. So let me try to use the ratio test for this guy. Yeah. Okay. So in order to use the ratio test, first, I will need to take the ratio between an plus 1 and an. So this is going to be my an plus 1, right? And this is my an. And what is this? Okay, so this is a complex fraction. So it's going to be n plus 1 over n times 1 over 2. Okay? And this is tending to what? Just one half. And this is clearly less than 1. So this is convergent. Okay. Isn't that amazing? And number 2. Okay, this time, let me try something even greater than this one, the previous example. What do you think about this guy? Yeah, we know this guy was the first one. First example was convergent. But this one is even greater than this because, well, the numerator is increasing even faster than before. But in this case, we still know that this one should be convergent, right? Because, even though this guy looks quite, even though this guy looks increasing even greater than this one, but this is just merely a polynomial. A polynomial of degree million, will be eventually increasing slower than the exponential function. So, and I can also prove that this one is convergent by using the ratio test. But this is my n plus 1, n plus 1, n plus 1, sorry, an plus 1 always goes to the top of the fraction. And an goes to the bottom of the fraction. So as n to the infinity, so this is n plus 1 everything to the fifth by n to the fifth times this 1 over 2. So this is still 1 over 2, and which is clearly less than 1, so this one is also convergent. Okay, so this one looks even crazier than before. Well, first, this is an alternating series, right? And the numerator is exponential function, and denominator is factorial function. And we know that the factorial function is increasing even faster than the exponential function. So in this case, I am pretty sure that this one should be convergent. Right? I don't know. Well, I mean, the point is, whenever your series contains some sort of factorial function, then the ratio test is working best. Because when you use the ratio test, then the ratio between an plus 1 over an will definitely make factorial function even simpler than before. So limit n to the infinity minus 2 to the n, to the n plus 1 over n plus 1 factorial. This is an plus 1, and minus 2 to the n's over n factorial. This is an. And we're taking the absolute values. So since absolute values, so it is now safe to say we can safely get rid of these plus or minus alternating factors. So they're just going to be 2 times n factorial over n plus 1 factorial, right? But you can simplify this. This is simply just 1 over n plus 1. And this is tending to 0. Right? And 0 is clearly less than 1. So therefore, this is convergent. Okay. Now things are different. On the top we have the exponential, and on the bottom we have factorial function. Polynomial function. And so it looks like this one should be divergent, right? Increasing too fast. And actually it is, because by the ratio test, 2 to the n plus 1 over n plus 1 factorial, n plus 1 everything squared over 2 to the n squared. Simplifying this, this is 2 times n over n plus 1 everything squared. Okay. And this is tending to 2, which is greater than 1. So therefore, this one should be divergent. Okay. Yeah, I have 2 minutes. Sorry. Just 1 over n squared. Well, if the denominator is just the linear polynomial, then it is safe to say this guy is divergent because this is harmonic series. But this time around, this is not a linear polynomial. This is a degree 2 quadratic polynomial, lies in the bottom of the fraction, right? So this one should be, well, decreasing even faster than the regular harmonic series. What do you think about this? Is it convergent or divergent? This is actually a hard question. Well, I mean, this is actually convergent. But well, if you try to use the ratio test towards this series, then 1 over n plus 1 squared and 1 over n squared, absolute values. And it turns out this is just n over n plus 1 everything squared, and this is 1. So that means the ratio test cannot say anything about the convergence or divergence of the series. So I mean, this kind of series is the hardest kind of all. So this guy, the convergence of divergence, this guy cannot be determined by using the limit test, comparison test or the limit comparison test, and definitely we cannot use the alternating series theorem, and then also we cannot use the ratio test. So this is one of the hardest kind. We're gonna go back to this series later on. But for now, this is the end of the story, and see you next time.